All right, so we'll be using this traffic stop data today, which actually I'm going to start that down because it's kind of big. I'll kind of work through one more Excel example with you. I think it's kind of interesting. I'll relate that to what some other people have found. But I also wanted to mention some stuff on the top. So we won't be having class on Friday, so I thought I was going to be able to travel for a conference and stay here for classes, but it's looking like that's not going to work. So we won't be able, I won't be meeting with you on Friday in class, although I'll be putting up a bunch of videos this afternoon of me working through practice exam A, so every single problem on practice exam A. And then Monday, next week of finals week, we'll kind of meet our typical time and location, and I'll just be doing exam review. All right, so I'll be working through more of the practice exam problems, kind of focusing on B. We'll get through a little bit of B today, do a little bit of review, practice exam review for the linear regression stuff today. And then on Monday, I'll probably try to go back and do more two population hypothesis testing examples, work through a lot of those. The fifth Connect and Excel assignment, are right here. So that fifth Connect and Excel assignment, I'll kind of still be in my office hours today and tomorrow. If you have any questions, last minute questions on those are due by the end of the day Friday. So I'll try to get those graded pretty early next week. As soon as the due dates pass this weekend, I'll post the answer key up for that fifth Excel assignment. So you'll have that as an additional study tool. I'll move this online quiz so it kind of is factored into your grade and then drop the 3 lowest. So that change should show up on Canvas later today. And then I'll also, I believe this is a different section. I have one more section I still have to grade their Excel assignment, but for you guys, if I remember correctly, I've got it graded and I've already moved them into the category so that they're now being kind of counted towards your grade. So if you don't do the fifth Excel and Connect assignment, whatever you see for your current grade, right? It's counting those, where are they at? It's counting the first 4 right now. If you don't do the fifth one, it will get dropped and you would have whatever grade from the first 4, right? If you're missing one of these first 4 and you do the fifth one, well, it would then kind of replace, right, your lowest Excel grade. So obviously that can't occur until past the due date. So it sounded like it was my phone. I was going to say, what in the world? So, that those changes should occur after the due date for those as well. Okay, and then we'll talk a little bit. I'll point that out again on Monday, and talk a little bit more about the specifics of the exam on Monday. But right, usually we have 20 questions for a 50-minute exam, so I should probably do something like 40 questions, right? If we've got 2 hours. But I'm not that mean. So we're just going to have, it'll be 30 questions. So a little bit longer, right? Not twice as long, and you'll have more than twice as much time. So timing should not be an issue at all in this final. Okay. I think that's all the housekeeping stuff I want to get out of the way before we jump into material. So any questions from me before we get going? Yeah. Yep. So that's why do you guys know how, did I go over how to find the final exam schedule, you guys? Yes? No? All right. Well, even if I did, a reminder. So Google search Ball State final exam, or actually I forgot what word in the final exam schedule. So the reason why we meet in the same location and time is so that there's no overlap. So if you come down here, I think this is it. Nope. What? I thought that pops up if I Google search that. Here. Let's do the academic calendar. That's what I want here. Well, I thought when I Google search that should pop right up. No, why can't I find it? Hold on, Ball State. Let's see if it pops up over here. There we go. I clicked the wrong one. So if you search final exam schedule and under that Ball State link, there's like 2. If you select this guidelines one, it has this schedule. So like if you have a 3 credit hour course and it meets at 10 on Monday, Wednesday, Friday, the exam is Wednesday at 9:45. So that's when our exam is, right? And then you could kind of figure out, any other class you had, what their kind of reserved time slot are. That way you don't have any other, final exams kind of crossing over each other. So our final is Wednesday at 9:45. Okay. And that's also on the syllabus. That's just under the files tab here. I kind of have that date and that syllabus as well. Okay. Any questions before jumping into material? So I've got this Excel document, which is this traffic stop data. So it says it comes from a large city in Texas, in Southeast Texas. My guess is it's Houston. But we've got a bunch of different variables here. So the month of the stop, the officer's race, the reason for the stop, whether or not the officer was male. That's just a 1 if they were, 0 if not. Officer's years of service. We've got driver's race. Each number represents a different racial category. I've got whether or not the driver was male, the driver's age, whether the vehicle was searched, and what was the result of the stop. Okay. So what I'm kind of interested in here is going to be something like this. And I'll show you some little data management or data cleaning stuff here in a second. But that reason for the stop, one of the numbers in there represented that a ticket was issued, right? Or sorry, the result of the stop, not reason. So the result of the traffic stop was that a ticket was issued. And this was just would be a 1 variable if the ticket was issued, a 0 if not. I then might be interested in something like, well, if the driver is white, right, is there any change in the predicted Y variable or in the predicted probability that that driver is issued a ticket? If this is anything other than 0, well, then we have evidence that drivers are being treated differently based on their race. Right? And we can control for things like, what was the officer's race, right? So we could do, was the officer white versus a non-white officer? Then I could do something that's a little bit outside the scope of this class. Wouldn't necessarily put this on the exam, but I do want to show you kind of the power of regression analysis and some interesting things that we could do. So I'm then going to include a third variable, which is I'm actually going to create this and simply multiply that officer being white variable by the driver being white variable, right? So we would call this an interaction term. I've created this variable that is an interaction of 2 other variables. So what this coefficient would tell me is the additional change in my Y variable, or the additional change in the probability a ticket is issued if the officer is white when the driver is also white, right? So this would show, so it's kind of a weak term, but same race preference, right? If I see that there's any difference in the issuing of tickets for this combination of when the officer and driver are both white, this would tell me that white officers are issuing tickets to white drivers at a different rate than non-white drivers. So if this is negative, right, that would mean that when the officer is white and the driver is white, that there's a decrease in the probability a ticket is issued, or decrease in the probability that a white driver gets a ticket from a white officer. That would mean that a non-white driver would get a ticket at a higher rate. Right? So this kind of interaction term will allow us to kind of pick up this same race preference or discrimination. Okay? So that's eventually what we're going to try to get to. So I have a little bit of data cleaning to do because I don't have that ticket variable, right? But I do have the result of the stop, right? And I had this Word document that I brought along with me to kind of help decipher this data. So here it kind of has a description of every variable. And notice down here, the result of the stop, a 5 represents an arrest, a 4 represents a ticket was issued or a citation was issued. So I'm actually going to create 2 variables, not just whether or not a ticket was issued, but whether or not an arrest occurred. Okay. So I'm going to call this ticket and arrest. I'm going to zoom in so we can see what I'm doing a little bit better. And I can create these indicator variables from the original variable that downloaded with the data, which is the result of the stop, by using that if statement, right? Because I just want to create this variable and I want to put a 1 every time the result of the stop is a 4 and a 0 if not. So I'm going to say, look, if the result of the stop if that variable is equal to 4, well, comma, that represented a ticket was issued, so I want to put a 1. If that's not a 4, that was, a verbal warning or written something, well, a ticket wasn't issued in those situations, so I want to put a 0. Right? So this variable, or this if statement, will only put a 1 if the result of the stop was equal to a 4, 0 if not, right? And that's because in that Word document, a 4 represented that a citation or a ticket was issued. So I'm going to hit enter there. And then I'm going to go down to that bottom right corner, double left click, and that'll fill this in for every observation I have in the data set. And then I'm going to do the same thing for this, creating this arrest variable. And you don't have to do this in the 5th Excel assignment, you won't ever have to kind of create these, but maybe outside, as a kind of a course that you take after this, right? So I can do the same thing and create this arrest variable and say, look, if the result of this stop was a 5 in the data, that represented an arrest occurred. So comma 1, if that's true, comma 0, if it's not true. So every time there's a 5 for the result of the stop, that represented an arrest was made. So I'm putting a 1 in there for that arrest variable. Every other number didn't represent there wasn't an arrest, so I'll put a 0 in there. Once again, double left click. Now I've got kind of these 2 variables. So I just said, if the result of the stop variable is equal to 5, comma, put a 1 if that's true, comma, 0 if it's not. And then I double left click here when it's a black kind of plus sign, and that should copy it all the way down to the last observation. What were the other variables I wanted? So I wanted, was the driver white and was the officer white? So I've got these race variables. I go back to my Word document. Looks like here, where was it? The value of 5 represents white. So I can go to, and the same thing for the drivers and officers race. So I'm going to do the same thing here and say, okay, look, if this driver race variable is equal to 5, comma, put a 1 if that's true, comma, put a 0 if not. That's going to make this driver being white indicator variable 1 every time the driver's white, right? Because that was the number 5 in that original variable. So I'll copy that down. Now I've got that indicator. Same kind of thing for the officer being white. I've got the officer race variable over here. And I said, if that's equal to 5, comma, put a 1 because that represents the officer was white, comma, 0 if not. So you can use this if statement, and really you're just checking, you're using that original data to kind of create these indicator variables. Any questions on anything there? Like I said, I'm not going to make you manually go through and create these variables, but in practice, a lot of the times you do because this is how the data downloads. I'm then going to do my interaction term, which is the officer white and is the driver white, right? Is that combination happening? So the only time this is a 1 is if both of these indicators are 1, 0 every other situation. So I'm just going to take my driver being white, multiply by my officer being white, and then copy that down. Right? So the only situations where this is a 1 is when both the driver and the officer are white. Right? In other situations, that variable is a 0. So I now have those 3 variables that I wanted to kind of pick up on, is there some discrimination going on? Right? Are white drivers given tickets by non-white officers at different rates? Are white officers just issuing, right? I'm kind of controlling for the fact that white officers may just issue tickets at different rates. And then this interaction, that's where I'm going to pick up my discrimination. Okay? So another issue that we have when we're working in Excel is when I work on a regression, I have to include all of my X variables. They have to be right next to each other. So like I couldn't select these 3 columns, hold control and then select driver's age. It'll look like I could do that. But then when I'm in that regression tool and I hit OK, it'll give me an error. So I'm going to have to move all the other additional control variables that I want to put in my regression so that they're right next to these kind of race identifiers. So I've got driver's age and whether or not the driver was male. So I'm going to copy this, just drag it over. I'm not copying, sorry, I'm just dragging this over, just moving the columns in my data set. And then I want to also do whether or not the officer was male and the years of service. Right? So I'll drag this over. Now I've got all of my X variables in what they call, Excel calls it contiguous columns, right? So now we can actually run this regression and get some interesting results. So we'll go to our data tab, go over to data analysis, scroll down to regression. My Y variable I wanted was whether or not a ticket was issued. So I'll Control Shift, Command Shift on a Mac, hit the down arrow. So I've got 79,000 almost 80,000 observations. I'll then go to select my X variables, which is from driver being white all the way over to officer's years of service. Control Shift or Command Shift on a Mac, hit the down arrow. I've now got my X variables and my X variables and my Y variables selected. I selected the names of my variables. If I don't, actually, let me show you what happens if we don't. So let's say I just selected the data and I didn't actually select the names as well. So I don't select the labels. It'll run that regression, but it just calls the variables X variable 1, 2. Well, that's kind of annoying, right? I mean, I go back and look and see what the order was. So I'm just going to delete this because that's not what we want to do. What we actually want to do is include the entire column, including the name. Oh, come on, get out of here. And then here, we want to select those labels as well and just tell Excel, yeah, use these labels so I don't just see X1, X2, X3. So we're going to hit OK. I'm going to zoom in so we can look at this regression output. So before we even get to the coefficient estimates that we have here, our R squared is 0.03. So the proportion of a variation in whether or not a ticket was issued, the proportion of that variation we're explaining is like 0.03 or 3%. So we're missing a lot of important variables here, right? 97% of the variation we aren't accounting for. So we should be really concerned that we've got important omitted variable bias going on, and you know, our coefficients are really just evidence of correlation. So we scroll down, I'll kind of go through how we interpret some of these other variables, right? So before we look at the kind of race stuff, let's look at these down here, right? So first we'll start out with kind of a, I don't say easy one, but if we've got an indicator for whether or not the driver was male, right? When you think about the general interpretation is of a slope coefficient would be if the X variable goes up by 1 unit, predicted Y variable changes by whatever that estimate we have for the slope is. Okay? So if I've got this fourth variable, which was the driver male, well, that's just a 1, 0 variable. So a 1 unit increase is going from the 0 to the 1 group. So a male driver relative to a female driver, right? If I'm looking at a male driver relative to a female driver, going from that 0 to the 1, the change in the probability of being issued a ticket. Remember, we said when our dependent variable is 1, 0, the units, well, we don't have dollars or inches or anything. The units is really changes in the probability of belonging to that 1 group. So a male driver, so going from looking at a female to a male driver, the predicted change in the probability of getting a ticket would be whatever that coefficient B4 is. I think it's actually negative, or no, yeah, negative here. So male drivers are a little bit less likely, holding everything else in this regression constant, to be issued a ticket. And what levels is this significant at? So if we're looking at that p-value, we got 0.05, just above, a little bit higher than 0.05. So remember, in all of these regressions, we always assume that every slope coefficient is equal to 0. Because what we're trying to find is, well, is it not equal to 0? Is there a relationship between this X and Y variable? That's what we want to find. Stack the deck against ourselves, assume there is no relationship. All right, so we can kind of think about this. There is no relationship here. So then we then look at, okay, if our p-value is less than alpha, then I can reject that null. Or I can reject that there's no relationship, said differently, I found evidence that there is. So if our p-value is like 0.0509, that's only going to be less than our alpha of 0.1. So at the 10% significance level, we could reject the null, or say that there's a, reject that there's no relationship, or say we found evidence there is a relationship. Questions there before we keep moving? So if I look at this output, these are essentially p-values of 0 anytime we see e to the negative. So really everything, this p-value is so close to 0 that Excel rounds it to 0. So it can't really, everything here looks like it's significant. The only exception is kind of this gender identifier variable. It's not significant at our 1 or 5% levels, only the 10% level. I could then interpret something like driver's age. So here, what will a 1 unit change in our X variable be? The driver is 1 year older, right? So if the driver is 1 year older, the change or the predicted change in our Y variable, which was whether or not a ticket was issued. So the change in the probability a ticket is issued looks like goes down by 0.002. The probability a ticket is issued goes down a little bit. Now that might seem pretty small, but we said last class, that's just 1 year. What if we're looking at a driver being 20 years older? Well, if I know the effect of being 1 year older, I just scale that up by multiplying by whatever change I'm interested in, right? So if the driver is 20 years older, the decrease in the probability they're issued a ticket is about 0.049, right? Or 5% less likely to be issued a ticket. So it looks like age kind of does play a role here. Officers' years of service, just not going over these with a fine-tooth comb here, but it's kind of interesting. Notice here, when the officer's on the job longer, they actually issue more tickets, right? So maybe this is like they hate their job, right? They start not caring, they start giving more people tickets. But these are all kind of interpretations that we could make. What about our kind of race identifiers here? Okay. So we're going to control for whether or not the driver is white and control for whether or not the officer is white. So it looks like when the driver is white and then the officer would be non-white, because the only other situation where this would be equal to a 1 and this wouldn't be is when the driver is white but the officer isn't. So it looks like it's actually non-white officers are issuing tickets to white drivers at slightly higher rates, right? If the driver is white, the probability they get a ticket goes up. The predicted probability they get a ticket goes up by about 0.045 or 4.5%. And these are all very significant, right? We can reject that there's no relationship or that slope is equal to 0 at every single level. Now, the more interesting one we said was, well, I guess they're both interesting, right? But when the officer is white and the driver is also white, what's the kind of change in the predicted probability of ticket issue? So this would identify kind of a same race preference, or I guess, discrimination. So when the officer is white and the driver is also white, the change in the predicted change in the probability of being issued a ticket, that probability goes down by about 0.045. So white officers are less likely to issue tickets to white drivers, holding everything else in this regression constant. Okay? So it looks like we found some evidence that there's discrimination that's going on, right? White officers are treating white drivers slightly less, more punitive than non-white drivers here. So this is bad, right? We've identified from 80,000 traffic stop observations that there's some discrimination that's going on in the issuing of tickets. Right? And once again, that p-value is 0. So we can say this with a high level of confidence, very high levels of confidence. So that's not good, right? We don't like to see that. But if we go back to the data, I'd also created this arrest variable. So I'm going to go back to my data analysis tab, run another regression, and now I'm going to select this arrest variable as my dependent variable. Right? I'm going to include all the same controls, but now I want to try to predict whether or not this traffic stop resulted in an arrest. Okay? So now I'm going to hit OK. get some additional regression output, zoom in so we can see things. But one thing to notice is my R squared here is 0.01. So I couldn't explain a lot of the variation when it came to whether or not a ticket was issued. I can explain even less when it comes to whether or not an arrest was made during a traffic stop. Right? There's probably a lot of other factors out there, like, you know, the driver's previous arrest record, the driver's income, educational. Like, there's a ton of other things that we would want to have controls for. In fact, we're missing 99% of the variation that exists in this arrest variable. So we should be, you know, these are interesting results. We can talk about them as evidence of discrimination potentially, but we also have to remember we're just picking up evidence of correlations, and we have a lot of omitted variables here that we probably are causing a bias, right? So I come down here before we look at the race stuff. It's kind of interesting now. Looks like being a white driver, or sorry, being a male driver, when it came to issuing a ticket, it was actually they were less likely to get a ticket. But when it comes to whether or not they're arrested, much more likely to get arrested during a traffic stop, right? Now, you know, knowing, I don't know, males in their 20s, I'm not super surprised by this, right? And so we can also look at age. As the driver gets older, they're less likely to be arrested during a traffic stop. Once again, not overly surprised by that. Officers' years of service. This is kind of an interesting story. So when it came to whether or not a ticket was issued, we found a positive effect that when an officer was on the job longer, they more likely to issue a ticket, holding everything else in this regression constant. When it comes to arrest, an additional year being on the service actually decreases the probability that the officer arrests somebody during a traffic stop. So maybe this is evidence that, like, yeah, they're writing tickets at higher rates, but they're not like overreacting to situations, you know, that maybe are a little bit more tense and then resulting in an arrest in this traffic stop. So kind of an interesting result there. And then we'll look up here at our kind of interaction term where we said this is really allowing us to pick up this same race preference or discrimination. So when the officer is white and the driver is also white, it looks like they're a little bit less likely to be arrested during the traffic stop, right? The probability decreases by 0.002. Pretty small effect, but still a negative effect there. So we still see that, right? We said if this was negative, we're picking up there might be some discrimination going on, right? White officers might be treating white drivers a little bit more favorably than non-white drivers. However, that's the interpretation of our coefficient, but it's no longer statistically significant, right? A p-value of 0.2, that's not less than any of our benchmark alphas. In fact, I couldn't even reject the null here at the 80% confidence level, because 80% confidence would be a 20% significance level or an alpha of 0.2. So my p-value isn't even less than 0.2 here. So it does look like there's some evidence that maybe there's some discrimination going on with the arrests, but we can't say that at any statistically significant level, right? We can't say that at any significant level. We can reject the null. And if we can't reject the null, what we're really saying is we didn't find strong enough evidence to say that there's any relationship between this interaction term and whether or not we actually change this to arrest, right? And whether or not an arrest occurred during the traffic stop. So, you know, we found evidence that this was negative and at statistically significant levels when it came to writing a ticket, but not for whether or not an arrest occurred. So this is pretty much in line. I was trying to look this up between classes, and the guy's name is Roland Fryer, like genius dude. And I think he's at Harvard, but then I think that there was an issue there. So if you search Roland Fryer, police violence, kind of these scholarly articles, there's some studies you can kind of look up. It's a really interesting paper, and it kind of echoes what this data set, even though we're doing something that's a little bit more simplistic than what he does. We're kind of running some very simple regressions. He finds a similar thing, which is that when it comes to lethal police violence, so like if police officers do something during an arrest or during a traffic stop that results in the suspect's death, right, like a police shooting, he actually runs this regression in a very similar way, looking at that interaction term. And he also finds that kind of like our example when we were looking at arrest, that lethal police or use of lethal, I forget what they exactly call it, like, but basically the police is doing something that results in the suspect's death, that this is statistically no different from zero. That we find, I think he finds, I forget, it's like a small negative effect, but the p-value is very, very high. So you can't actually say that when the officer is white and the suspect is white, that there's any difference in the probability that the police interaction results in the death of the suspect. However, kind of like what we found in this data, what they do find is that when the officer is white and the suspect now is also white, right, that it's much more likely that police use non-lethal force, right? So they are treating non-white suspects much more harshly than white suspects, and that was statistically significant. When it came to lethal force, once you can control for all these other factors, and they've got way more data and way more variables than what the data set I showed you, that you actually see there's no difference in the interaction of white officers with white or non-white suspects when it comes to lethal or force or force that would result in the death of the suspect. So kind of good news, but also bad news at the same time, right? So maybe the idea of kind of lethal police interactions, we don't see a lot of evidence of discrimination looking at the data they were looking at. But when it comes to non-lethal force, there was significant effects there where police are treating non-white suspects much more harshly. But yeah, that kind of lines up with this data set. So I thought it was kind of an interesting thing to bring up. For the rest of class, let's go to this final exam form B. Okay. So I mentioned I'll be posting videos of the practice exam A, working through all this two population hypothesis testing stuff. But what I want to focus on today is kind of working through the linear regression part of this practice exam B. Okay. So I'll give you some Excel output. So these are all very questions that you could see on the exam. So we've got our dependent variable is wage measured in dollars per hour. So I'll eventually write this regression equation out for us. But the four variables that we're going to include as control variables or independent variables are years of education, years of experience on the job, age, and then this gender variable, which is a 1 if they're male, 0 if not. So what we're thinking about is we've got this regression where we've got wage, our intercept, education, we had all the other variables there, right? And the reason why is because I know the question asked specifically about education next, right? So, we include all of those control variables there on the right-hand side. So we run this regression and Excel gives us this output. Okay? So a couple of things that you could be asked questions about, even if they aren't questions on this practice exam. What percent of the variation in wages do these four variables explain? Well, the proportion of the variation they explain is 36 or 0.368 or 36.8% of the variation. It's how we interpret that R squared variable. So we're still not explaining about 63% of the variation. So there's still a lot of omitted variables here. So once again, we need to be cautious. These are just evidence of correlations between these X variables and this Y variable of wage. So what would my correct interpretation be for this education variable? Well, remember we said the slope coefficient interpretation would be a 1 unit increase in X is correlated with, or the predicted Y variable changes by. So is correlated with a beta 1, right? Either increase or decrease depending on if it's positive or negative change in our Y variable, right? So what would a 1 unit change be here? Well, 1 additional year of education is correlated with the predicted wage changing by whatever value we get from that regression. If I remember right, and we'll look at it here in a second, I think it's 1.233. So for each additional year of education, that would be correlated with a $1.23 increase in the hourly wage. That's how we would interpret that slope coefficient. So and then holding everything else in the regression constant here because we had multiple variables on the right-hand side. So holding everything else constant, every additional year of education is correlated with that $1.23 increase in hourly wage, right? That's how we would interpret that slope coefficient. What if I wanted to interpret this gender variable? Well, whenever I have a variable that's just 0, 1, it's always going to be looking at the 1 group relative to the 0, or going from the 0 group to the 1 group. Here's the predicted change in our Y variable, right? Or it's correlated with this change in our predicted Y variable. So here it was a 1 if male, 0 if not. So a male relative to a female, we would expect, or it's correlated with, or the predicted change in hourly wages that they go up by $2.29. This is kind of like picking up the that gender pay gap people like to talk about, right? A male relative to a female, we would expect the hourly wage to increase by $2.29, holding constant their education, their experience, and their age. Right? So that's how we kind of make these interpretations for our slope coefficients. If I then asked you to find the test statistic for age, well, I have this white box that's hiding them, so you can kind of see them here. But I'll pull up in that formula sheet. It's a PDF. So we've got all of our equations that we'll need for the final. And some of them we don't really need. Like this is how we would do it by hand. I said I'm never going to make you do it by hand, so you can kind of almost like ignore these. But one that we are going to be interested in is how do we calculate the test statistics for these slope coefficients or for the intercept, right? So whenever we're calculating test statistics, and here we want to calculate a test statistic for a sample coefficient, we're always going to take our estimate, our sample statistic, or here our coefficient estimate, subtract the assumed true value, and then we always divide by the standard deviation of whatever statistic we're looking at. Now, we had different ways of calculating that when we're looking at the difference in sample means, different sample proportions. Here, we're never going to have to do this by hand. Excel gives it to us as that standard error. So the standard error is really like a way that you can think about it. And there's a reason why we have different terminology, but it's kind of outside the scope. I mean, I'm not going to waste a lot of time on it. It's kind of getting outside the scope of this class. But you can think about that standard error is really like the standard deviation for that slope coefficient estimate that you have. Just like we usually divide by the standard deviation of our sample mean or our sample proportion. That's what that standard error represents. Now, I said earlier, we always start out assuming that these coefficients are equal to 0. Well, subtracting 0 doesn't change anything. That's why my test statistic ends up being just that slope coefficient divided by my standard error. Okay. So when I go back here, that's take that estimate you find for the slope coefficient divided by your standard error. So all I would do is take that age coefficient, negative 0.019, divided by that associated standard error of 0.083, and I should get something right around negative 1/4 or negative 0.25. Sure enough, negative 0.229 ends up being the exact answer. And I could do that for every single variable in this equation, right? Education, take its coefficient, divide it by its standard error. That's how I get the test statistic. Okay. Any questions there before we keep moving? So interpreting those slope coefficients, finding your test statistics. I could also have asked you, I think the next one is about the intercept maybe? No. But I'm going to add in 2 questions here. So one, how would I interpret the intercept? Well, I said the interpretation of the intercept is when all of my x variables are equal to 0, here's the expected or the predicted value of my y variable. And the reason why is because you think about, if I went through, once I have the slope estimates, I can plug them all in. And then if every single x variable was equal to 0, well, then anything times 0 is 0. The only thing I'm left with is the intercept. So when every x variable is equal to 0, the predicted y value, or here the predicted wage, would just be what that intercept is. So that's why we interpret the intercept the way that we do. Okay. So for a person that has 0 years of education, 0 experience, age 0, and they're female, right? We would expect the predicted wage, hourly wage, to be $8.68. Now, the interpretation will sometimes be very weird. Like you can't see someone who's 0 years of age, let alone working, let alone just even be a person. But kind of mentioned, and I'll draw a graph here in a second from our second example. Remember, it's just like that's the starting point of our line. Our line might be based off of data that's way over here, and we never see observations near that y-axis. But we still have to have a starting point for the line. So that's why the interpretation can get a little bit weird for the intercept. Okay. Any questions on that? I'm just kind of going through more examples. It's really the same things over and over, just in a slightly different context for this linear regression stuff. What if I asked about which variables other than the intercept could you say have a significant relationship with hourly wages here? So which variables could I say have a significant relationship with hourly wage? And let's say at the, sorry, I have to give you a level. Doesn't really matter here, at the 99% confidence level or at the 1% significance level. So alpha there would be 0.01. So what I'm looking to see are what variables have a p-value that's less than 0.01. So I'm looking here, education and experience both have p-values less than 0.01. So 0.005 is less than 0.01. So at the 1% significant level or 99% confidence level, I can reject the null. Well, the null is always that there's no relationship. So if I'm rejecting that there's no relationship, I'm saying there is a significant relationship. So looking at this p-value, education and experience have a significant relationship with wages. I can't say the same for age and gender, right? Those two p-values are not only are they not less than 0.01, they're not even less than 0.1, right? Even my kind of last benchmark value. So I can't say that they have a significant relationship with wage here based off of these estimates and these p-values. Is that clear how we can make those rejections? So is there any questions on that? So if I'm rejecting the null, I'm saying that there is a relationship. I'm rejecting that there's no relationship. Okay. I think that's, so we got a little bit of time left. I'll go through this one and kind of pick up on this on Monday. So another form I could kind of give you is, let's say I want to estimate the relationship between a child's birth weight and the mother's age. And I have birth weight as my dependent variable. So let's assume that I find the intercept coefficient is 3,524. How would I interpret that? Well, I'm just going to actually write this out. So if I've got birth weights here as my y variable, and I included what? Mother's age as my x variable here. I was just told that this was 3,524. So the way that we interpret the intercept is always, it's the predicted, or you can kind of think about, we could use the word expected here, same idea, value of y, whatever our y variable is, when all of our x variables are equal to 0. So here, it gets kind of a weird interpretation where if the mother's age is 0, the expected birth weight would be 3,524. And the reason why we find that is because when we look at mother's age, we don't see anything, we're not seeing really, really young people, right? We're not seeing any data here for the first however many years of someone's life, but that line still does have a point where it starts on that y-axis, right? We can trace that line, kind of its starting point back to the y-axis. So the expected birth weight of a mother who is 0, 3,524 grams, that would be how we interpret the intercept. Kind of a goofy interpretation, but that's because of the data is probably kind of is all over here on the right-hand side. I think the next problem says something like, assume that you find the slope coefficient is 2.54. So the next question doesn't ask you to interpret that, but if we wanted to, how would I interpret that slope coefficient of 2.54 on mother's age? Remember, for the slope coefficient, it's a 1-unit change in x is correlated with or changes the predicted value of y by whatever that slope coefficient is. So if a mother is 1 year older, we would expect or predict that the birth weight goes up by 2.54 grams. That's how we would interpret that slope coefficient. Any questions there? So I think the problem actually asks, you know, we find that slope coefficient and the researcher concludes that as a mother gets older, children are going to have a higher birth weight, right? So what's wrong with this logic? So especially with a very simple, naive linear regression where we haven't included multiple right-hand side variables, we're all, you know, or if we don't have an R squared of 1, we always need to be concerned that we're just picking up evidence of a correlation, right? So if I'm trying to make kind of causal relationship statements here, I can't do that. The regression is just evidence of a correlation. And in this situation, kind of explain it even more, it could be that as a mother gets older, they have an increased level of education or an increased income, both things that we know would also push birth weight up. So if we don't include those in our regression, that coefficient is going to be biased. It could be picking up the effect of these other things like education and income, which we know are also positively correlated with mother's age. Okay? So we have to be careful when we're making statements using regression output that we remember it's just evidence of a correlation. So an additional question I could ask you here, and I'm trying to get this idea of what we're doing with linear regression. I'm just going to rewrite this out a little bit. So let's say I wanted to come up with predictions for birth weight. Well, I could do that using my intercept coefficient value that I found and that slope coefficient value that was associated with mother's age, right? So all I'm doing is taking this regression, this linear regression equation. I've now got estimates for this line of best fit. So what I could now do is come up with predictions for maybe a mother who is 30 years old. All I would do, plug in that X value of 30. Now I've got a very simple equation, 3,524 plus 2.54 times 30. That would give me my predicted birth weight. Now, obviously, like I said, this is a naive regression. I've left out a lot of other important factors. But, you know, as I add in more variables, I would just have, you know, I don't know, what's another one we could do here? Kind of length of pregnancy, right? I could just add in additional variables. And now it's just, I need more information about this hypothetical person. So a mother is 30 years old, length of the pregnancy is, I don't know, 38 weeks, right? And I would just be plugging in, I'd have more coefficients, and I'd have to be plugging in more X values, but it would still be just a simple linear equation once I plug all my values in. Okay. This is going to be kind of similar when we did the GPA for the athlete, right? We had all of our coefficients. We just did a column where we did all these hypothetical X values, multiplied each coefficient by the hypothetical X value, and then added them all up. And don't forget the intercept, right? Any questions on that? Okay, so on Monday, we'll kind of go through the rest of these linear regression questions, as well as go back and work on some of this two population hypothesis testing stuff. I'll get up those little videos that are me kind of working through all of the practice exam A questions this afternoon. Other than that, if there aren't any questions for me, I'll see you guys on Monday.